So you should all be a little more comfortable now with matrices, now that you've had to do some stuff for your homework. So we're going to have a final session today about matrices, and we're going to discuss it in the context of linear differential equations. So in the past few sessions, we have been looking at systems of linear difference equations, and then also extending it to nonlinear equations in the context of our Fisheries model, where the first equation we made nonlinear by introducing a stock recruitment relationship. So if we go back to the Leslie matrix equation, let me use black. We're talking about a model x at t plus 1 is L times xt, where we had defined the vector x to consist of elements x1, x2, xn. And we found out that we could understand the behavior of this equation as time proceeds, its asymptotic behavior, if we knew something about the eigenvalues and eigenvectors of the matrix. So what is it that we have to know about this matrix L and its eigenvalues and eigenvectors in order to be able to say something interesting? So what do we talked about something called the Perrin-Frobenius theorem, which is a fancy name for a theorem, because the people who worked on it were mathematicians by the name of Perrin and Frobenius. So why was it useful to know something about the eigenvalues and eigenvectors of L? The stable H structure, yeah. So it would tell us something about how the population grows and what the stable H structure would be if this matrix was something called a primitive matrix, and it was positive primitive matrix. Okay. So we find the eigenvalues and eigenvectors, or we find just the dominant eigenvalue and the corresponding eigenvector that tells us something about what the solution is going to do. And this here is a difference equation. Now we're going to move on and we're going to talk about differential equations. Now in the same way that at the beginning of the class we talked about the difference equation, linear difference equation, and a linear differential equation, and also we extended the idea to be a non-homogeneous equation. So first we looked at the homogeneous equation and then the non-homogeneous equation. And in fact, we looked at an equation like this that was important in understanding the growth of individuals, their length. What do we call that equation? The von Bertalanffy equation, remember? Okay. So we had a discrete and a continuous form. What we're going to do now is we're going to have a look at also the continuous vector equations, dx dt equals ax. We'll call this the homogeneous case. And dx dt equals ax plus b. And this is the general linear case. And this is the homogeneous linear case. And we're going to focus on the case in 2 dimensions where we're going to represent the vector x. So when x is written as a vector, I write it as boldface in the text, or I underline it on the board. It consists of 2 elements, x and y. And the matrix A is a 2x2 matrix, A, B, C, D. And the vector B has arbitrary elements, B1 and B2. Now, unfortunately, in some of this, these names appear in different roles. So here I'm calling B this element of the matrix, capital A, and here I'm calling B a vector. When I write B like that, then I'll write it as B1 and B2, which is not the same B as that. And in order to avoid confusion in some of this presentation, in the calculus text, you'll find I talk about constants A and B, but here I'm going to talk about constants alpha and beta. So when you see a B on the page, it's not necessarily the same B that you saw on a previous page. It's unique to either the example or the theory that I'm discussing as it's contained in a statement of a theorem or something. And it's not the same B in the previous example that was used to represent some arbitrary constant. Okay, so don't get confused about that. Okay, so do you remember what the solution to dx dt equals ax and x at time 0? Do you remember what the solution to that is? What is it? Exactly. Except it's a, not r. x0 e to the at. So exponentials come in, and the exponentials in this case relate to that constant a. Now when we come to 2 dimensions, what will happen is I'll get 2 exponential terms. In 3 dimensions, I'll get 3 exponential terms. These exponential terms, the rate arguments are now given in terms of what, do you think? If I've got a 2x2 matrix, then the 2 important numbers associated with the matrix, what are they? The determinant tells me that's one number, and it tells me whether I can invert it or not. But going to the next step, beyond the determinant, the 2 numbers that characterize a matrix. A 2x2. 3 numbers that characterize a 3x3. The word is characterize. What do I call character? Eigenvalues and eigenvectors. So it's the characteristic values. The characteristic values. So if I drop the eigenvalue and eigenvector, you'll probably be a lot happier and not freak out. But if you go through the math literature, that's the word that's used. So both words that are used. Okay. So now I'm going to claim something. Well, firstly, we'll just recall that under these definitions over here, this is the same as writing down dx1 dt is ax1 plus bx2, this equation over here. and dx2 dt is cx1 plus dx2. Now what I'm going to do is I'm going to give this a different name. I'm going to give this a name k, just on the board over here. It won't be in the notes, just so that. And if we go to this equation, then it's like adding k1 and k2. I don't want to call it b1 and b2 because I've already got a b there. But so be it. Okay? Nobody laughed at my pun. Makes me very sad. Okay. So you understand this problem with running out of letters and names to call things. Okay. So when I write down something like this, it's a series of equations that look like this. This is the homogeneous case is when these are 0. The general case is when these are non-zero. Okay. So it's all about keeping a perspective and knowing what I'm doing and not being confused or overwhelmed by the notation. And again, if I only ever worked in 2 dimensions, I would never have bothered with this. The reason why I write this down is because it works in n dimensions. So we saw that for the Leslie matrix model, it was useful to write it in this form if I have maybe 10 H classes or 20 H classes, because I don't want to write out 20 equations. I write it down in this very compact notation. I know exactly what I'm talking about, so I want you to get used to the notation. So now we have a theorem about the solution. So we know how to write down the solution to this very simple equation here. But what I want to be able to do is write down the solution to this equation over here. And I'm going to do it in 2 dimensions, but later on I'll show you that it generalizes to n dimensions, and I can write down the solution straight away. As long as I know what the eigenvalues and eigenvectors, or characteristic values and characteristic vectors of the matrix A are, then I can go straight away. So in 2 dimensions, if I have a matrix A, then in order to characterize it, so the characteristics of the eigensystem is that I can write down the eigenvalues and eigenvectors. So I'm going to call the first eigenvalue lambda and its corresponding vector v, and the second eigenvalue mu and its corresponding. So this is eigenvalue slash vector 1, and this is eigenvalue slash vector 2. So as soon as I see the matrix, I say, aha, if I'm going to understand what's going on with this equation, first thing I need to do is find the characteristic values of A and the corresponding characteristic vectors. Is everybody happy about this? Okay. So we have a theorem called 8.4, and I'll put it up in a minute, but I'm just going to write down the solution to begin with. So what I'm going to claim is that if I know this, and I'm going to say provided, so this is only provided lambda is not equal to mu. If lambda is equal to mu, it's a bit more complicated. Then I can write down the solution, and I see in my notes that I'm actually using u and v, u over here, not x. And the reason why I'm using u is because I'm calling the elements of u x and y. I'm going to call it u, and u has elements x and y. And so this equation would be u1, u2. In n dimensions, I'll just call it x and have x1, x2, x3. I'm going to call it u now. Oh, sorry, I'm calling these x and y, so that gets rid of this. x, y, x, y, x, and y. So if I have a look at this equation over here, I say, okay, what's its eigenvalues and eigenvectors? That's what it is. So then I can write down the solution. Now the solution is u, the vector u is a function of time. And there's going to be 2 arbitrary constants. So the solution is going to be for constants alpha and beta. So I've got these 2 constants. And these 2 constants will be determined by making sure that I satisfy the initial value. So if I'm given an initial value over here, u at time 0 is given. So I'm given the initial value, then I can find what these constants are. If I'm not given the initial value, I just have to leave the constants there until I am given an initial value. So it's alpha times e to the lambda t multiplied by the first eigenvector plus beta times e to the mu t times the second eigenvector. So when I write down this, it means that I'm writing down 2 equations in 2 dimensions, because this is 2 elements. This is a scalar value multiplied by a vector with 2 elements. This is a scalar value. This scalar value changes with time. It changes with time as influenced by the value of lambda, and this changes with time as influenced by the value of mu. Alpha and beta are arbitrary constants. And how do I calculate alpha and beta? Well, if I'm given u at time 0, then I say at time 0, I can write this equation down. E to the lambda 0 is e to the 0, which is 1. So alpha times the eigenvector v plus beta times the eigenvector w must be equal to this vector u. Does everybody understand that? So it's fairly simple. If this is the solution, then the solution must satisfy the initial condition. If the initial condition is given, the initial condition consists of 2 values, the first element of u and the second element of u. So does everybody understand that? It's almost like what I'm saying is that in 1 dimension, x of t equals e to the a t. In 2 dimensions, it's like saying x of t is equal to some constant, I'll call it c1, e to the lambda t, plus c2, e to the mu t. Y of t is equal to some constant C3 equal to the lambda t plus C4 e to the mu t. So in one dimension, I express the solution, and there's a constant here that will be determined by the initial condition. So there the constant's just equal to the initial condition. Here, these constants, C1, C2, C3, and C4, are a little more complicated because you see they're made out of two things. They're made out of an alpha, and I have to pick up the elements of the eigenvectors over here. So if you actually wrote all this out in detail, then you'd actually see how the C1, C2, C3, and C4 are made up of the alpha and the elements of the eigenvectors. I don't want to sort of go through all this stuff. What I want to do is give you the general idea. The general idea is that if I went to 3 dimensions, so if I went to a 3 by 3 system, and I said I had a vector x equal to x1, x2, x3, and a matrix A with eigenvalues lambda 1, lambda 2, and lambda 3. So you'll often see this in mathematics, that in 2 dimensions, we sometimes don't use the subscripts. I say U has elements x and y. In 3 dimensions, that gets a bit overwhelming. So I now just go back to the notation. Boldface x has elements x1, x2, x3. The eigenvalues now are lambda 1, lambda 2, lambda 3. So that's how people usually work in 3 dimensions and higher. But in 2 dimensions, people sometimes give them specific names and avoid having indices. Okay, so don't get confused about that. Now in 3 dimensions, the solution would look something like this. x1 at t is c1 e to the lambda 1 of t plus c2 e to the lambda 2t plus c3 e to the lambda 3t. And x2t would be equal to, now going to come in another constant, c4 equal to the lambda 1t plus c5 e to the lambda 2t plus c6 e to the lambda 3t. And x3 of t would be equal to c7 e to the lambda 1 times t plus c8 e to the lambda 2t plus c9 e to the lambda 3t. So the general solution in 1 dimension looks like this. In 2 dimensions, it looks like this. In 3 dimensions, it looks like this. Now you say, what are the C1, C2, C3, C4, 5, 6, 7, 8, 9? What they are is they're a combination of constants that are used to fit the initial condition, 3 constants that are used to fit the initial condition in 3 dimensions, plus the 3-dimensional vectors that are the eigenvectors as well. So this is beginning to overwhelm your mind in terms of the details, but the pattern is simple. Does everybody get the pattern? Okay. And so in order to solve these equations analytically, we find the eigenvalues and eigenvectors. However, if you've got something like, you might say to me, why do I bother to have a theory when I can just when I can just simulate the equations and see what happens? So why do you think a theory exists? We bother with a theory. Yeah? Yeah, well, it sort of gives us an insight into some structure of how these things work so we can get an idea of what's possible, what's not possible, without having to simulate things. We don't need to simulate things. We know generally that, okay, it's going to be a combination of exponential functions. There's going to be no nonlinear or funny things going on. It's just going to be, and it tells us how many exponential functions we're combining, and we just have to find those. But the real answer is that this theory was developed before we had computers. And so without having computers, it was hard to understand what was going on. But now that we've got computers, why do we bother? It's because it's not just about generating numbers. If you have a look at the number system is about natural numbers, or counting numbers, integers, positive and negative numbers, rational numbers, irrational numbers. And if you look at the integers, then they're different kind of integers. They're prime numbers and non-prime numbers. And so if I took this attitude and I said, I don't really care about the theory of numbers, they're just numbers and I can multiply, divide, and so on, then I wouldn't understand how prime numbers are used in cryptography. So prime numbers are essential to cryptography, and cryptography is essential to what in our everyday life? Yeah, data exchange. And no more important data exchange than exchanging data about how much money I'm going to pay you. You don't want somebody to hijack that and then take all your money out of your bank account. So everything is encoded, and people use the theory of prime numbers to encode them. But people also use the theory of differential equations and linear differential equations to understand how dynamical systems behave. So it allows us to do a lot of things. It allows us to see the forest for the trees. So when you do numerical simulation, you're just in the weeds and in the trees, and you don't have a sense of what the forest looks like. This gives you a sense of what the forest looks like. Do you agree with this metaphor or not?